Time history analysis subjects the structure to recorded or synthetic ground motion acceleration histories integrated directly through the nonlinear model. This gives the structure's actual dynamic response, displacement, drift, member force, and acceleration time histories. The window is organized around 5 stages, generally worked through in order, selecting ground motions, generating a target spectrum, scaling the records to that spectrum, injecting the resulting analysis code, and running it in parallel. This video goes through all 5 load ground motions except TXT, 8T2, or DAT acceleration record files. Each file selected is copied into the project's ground motions folder and converted automatically into the format OpenSees reads. Number of data points and time step are extracted automatically from the file. These aren't values you enter. They're read directly from the record. Every imported record shows in the ground motion list and in the time history graph. Ground motions need to be loaded here before anything in the next stages can happen. Peer Database opens the Peer NGA West 2 Strong Ground Motion database in your browser. This is a direct link to their site, not an in-application search. Find and download records there, then bring them in with load ground motions. Generate Target Spectrum in the Target Spectrum section opens its own window. This builds the response spectrum the ground motions will later be scaled to. 2 ways to get a spectrum here. Generate one from a recognized design code or import a predefined one as a CSV with period and SA columns matching the format this window itself saves. 5 design codes are available. Each brings its own governing parameters once selected. Eurocode 8 uses design ground acceleration, soil factor, periods, and behavior factor. ASCE 7 uses spectral accelerations at short and 1-second periods, site coefficients, and for the reduced design spectrum, response modification and importance factors. The Australian, Chinese, and Japanese codes each have their own equivalent parameter sets specific to their respective standards. Spectrum type matters. Regardless of code, elastic record selection gives the full elastic spectrum used for selecting and scaling ground motions. Design reduced gives the code reduced design spectrum instead. With max period set, press the Generate Spectrum button and it will build or rebuilds the target spectrum. The result populates in the table directly. It is editable by hand if a manual correction is needed. Add new row extends it, and the graph updates live as the table changes. Title and axis labels are editable here too, for whenever the plot gets exported or reported. Save Spectrum writes it as a CSV into the project's Target Spectra folder, the same folder the Time History Analysis window reads from, so it becomes available there immediately. Back in the main window, the Target Spectrum dropdown refreshes itself the moment you save, and the new spectrum appears ready to select. If it doesn't show up, the refresh button next to the dropdown pulls it in manually. Scaling adjusts each ground motion's intensity to match a target spectrum over a period range relevant to the structure rather than applying each record at its recorded, as is intensity. Every loaded seismic record is checked by default here. Uncheck any you want excluded from this particular scaling run. 4 scaling methods. Mean spectrum match scales the set's mean spectrum to the target. Individual spectrum match scales each record on its own to best match the target. PGA match scales each record so its peak ground acceleration matches the target. All 3 of those need a target spectrum selected. User scale factor is the exception, one manually specified factor, applied directly to every checked record, bypassing spectrum matching entirely, no target spectrum required. Target ratio sets what percentage of the target spectrum to scale toward, useful for code-specified levels expressed as a fraction or multiple of the target, such as a requirement that the average spectrum not fall below a set percentage over the period range. Spectrum sets where the pseudo-spectral acceleration or the elastic spectrum is used. T1, the structure's fundamental period, serves as the reference for that period range and feeds the matching calculation directly. Scale ground motions runs the matching. This can take several minutes depending on how many records are checked. That's expected, not a stall. Scaling results lists every scaled record, its name, the scale factor applied, original and scaled PGA, and a status column confirming success or flagging a problem. The response spectrum graph plots every scaled record spectrum against the target, so the match can be confirmed visually before moving on to code injection. Ground motion statistics summarizes how well the scaled set as a whole matches the target. This is the check that matters beyond just confirming scaling completed without error. Once ground motions are scaled, Inject into TCL opens a dedicated window for turning the selections into analysis code. 3 direction groups X, Y, and Z, each with its own enable checkbox, all on by default. Unchecking a direction disables and excludes its table from the generated code entirely. Each enabled direction gets its own table listing every scaled record. Tick whichever records you want applied in that direction. Inspect members optional adds per member recorders feeding the information for the member inspector window. Press refresh button to generate the code into the code viewer. By default, this application assigned 2 scale factors as 1 and 2. If you need to run several scale factors in one analysis, add all required scale factors in the TCL code. Review it here and make any manual additions like those extra IDA intensity levels before moving on. Insert TCL adds the verified code to the code editor, save the file, then run OpenSees to execute it. Parallel processing is configured from this same window. Running many ground motions one at a time is slow. This runs several OpenSees analyses simultaneously, one per available processor core, so a full set completes far faster than sequentially. Directions, ground motions, and inspect members are selected exactly as for a normal run. Ticking Enable Parallel Processing reveals the processor's selector pre-filled to one core fewer than the machine's total logical core count, leaving capacity for the operating system. This can be lowered further to keep the machine responsive for other work during the run. Refresh generates the code the same way as before. Scale factors can still be adjusted here just like a non-parallel run. Run Parallel opens the parallel processing monitor, tracking the run live. Each processor core gets its own card, a status for pending, running, done, failed, or killed, a progress bar for that worker's share, which ground motion and scale factor it's currently running, completed task count, elapsed time, and process ID. If the monitor gets closed after the code's already inserted, select Parallel Processing from View and it reopens at any time. It reattaches to the run in progress or shows the last completed run's final state without needing to start over. Working order, in summary: load ground motions, generate or import a target spectrum, scale the records to it, inject the resulting code sequentially or in parallel, then run the analysis.